engineer and has been a Lustre developer for just a little longer. His focus shifted toward Robinhood, but he is also interested in the whole HSM code in Lustre.
Contrôle L.
All right. Thank you for the introduction. Good afternoon, everyone. Today, I'd like to present to you the various progresses I made on RobinHood-v4. At this point, I suppose that most of you have heard about Robinhood, maybe even tried it. But just in case you haven't, here goes. So what is Robinhood? Basically, Robinhood is a system that mirrors the file system's metadata and makes it queryable. You might ask why that is and what's the point? Well, the mirroring part allows you to have a read replica of your file system's metadata. That means that if you have to run statistics and diagnostics, you can do this on the mirror, on the Robinhood mirror, and not impact your production servers. Obviously, the mirror can also be used as a snapshotting services, and the main use case for snapshotting is usually to do disaster recovery. This is not implemented in Robinhood, and this is mostly theoretical. The querying part, you might be thinking, like, a file system is already queryable. Yeah, but the best you can do on a file system is ask it, what can you tell me about this file, or this directory? You can't, for example, ask it, all right, what are the 10 biggest files that you manage? So file systems, in this sense, lack a bit of expressiveness in the queries that you can run on them, metadata-wise. The way you do this on a file system is you have to traverse it all and remember the biggest files you see. So obviously, this is neither performant or efficient. And that's where Robinhood comes in. Robinhood provides all of these, better expressiveness and performance. And this all comes from where Robinhood stores the metadata of your file system. And that, in the Robinhood semantics, is called a backend. Up until RobinHood-v3, that backend was a MariaDB database. And we realized in production that this database was becoming more and more of a bottleneck. So we decided we wanted to switch technologies and use something else, but we had to decide what exactly to use. We knew we wanted something that would scale better, so we oriented our search towards distributed databases, and at this point there were two obvious candidates, which were PostgreSQL and MongoDB. There were others, but those are the two that we were most interested in. We decided to pick MongoDB because, well, for very practical reasons, mostly just because I know a little bit more about MongoDB than PostgreSQL, and since I'm the one working on it, I decided to start with MongoDB. And then we looked at the code, and we started to think about how we were going to switch from MariaDB to MongoDB. And it turns out that this is very hard work to do, and we decided that if we were to do this, we would be able to support not only MongoDB, but all of the kinds of database system, and even more than just database systems. For example, with RobinHood-v4, we want to be able to support file system as a backend for Robinhood. The way to do this is to put the backend behind a C API, an interface, at which point it doesn't really matter that the backend is distributed or not. What you need to do to support a backend in Robinhood is implement this C API, which is basically a set of operations to push data in the backend and pull data out. And so you can do this for MongoDB, MariaDB, or even file systems. After you do that, you can actually plug in different applications, three of which I'm going to present to you right now. So, applications. The first one that you're probably going to use if you ever try RobinHood-v4 is RBH Sync. So what does it do? RBH Sync synchronizes two Robinhood backends with one another, It's very much like rsync, but for Robinhood backends. Here is the usage, classical CLI command for RBH sync. So much like rsync, you give it a source and a destination, and it synchronizes the destination with the source. But the source is not really that simple. This is an example of what it would look like in reality. So the two parts, the RBH, colon, POSIX, etc., is what I call a Robinhood URI. At this point, I suppose it's useful to explain what a URI is. A URI means Uniform Resource Identifier. It's defined in the RFC 3986, and its basic syntax looks like scheme, colon, a bunch of things that are optional, and a path. Robinhood actually mostly uses only the path and the scheme, but let's look at what it looks like usually. This is a URL, which is a particular example of your URI, and if we decompose it into its different parts, the HTTPS is the scheme, the example.com is the hostname. We know this is the hostname and not the path like test is afterwards, because there is a leading / in front of example.com. So that means that what comes afterwards is going to be a hostname and not the full path. With a Robinhood URI, for example, this one, the scheme is RBH. That means that the following, the rest of the URI is to be interpreted as a Robinhood URI. And since there is no / the whole thing is just a path in this URI semantics. And it has the meaning that Robinhood associates with it. If we decompose it further, the Mongo part tells you what type of backend you are referring to. And the Scratch part tells you the name of the file system that you're actually talking about with this URI. You can add a special part of this. This is called a fragment. This is the same thing that you see in a URL when you go to a site and you have the # with the ID of an HTML element, and your browser knows that it has to render the page starting at this particular HTML node. Well, in Robinhood, it's a tiny bit different. Here, the fragment has the meaning of a path in your file system. Sorry. And so, yeah, basically, the URI without the fragment part means it refers to a whole backend, while with the fragment part, it only refers to a particular entry in that very backend. And that's actually useful. It allows you to do things like this. It allows you to sync a particular subtree in your file system with a Robinhood backend. Visually, that would look like this. So this URI, the RBH POSIX, I forgot to mention that here POSIX means that you use the POSIX Robinhood backend, which is basically a real file system on top of which you implemented the C API that I mentioned previously. So when you do the previous command, what you do is you scan your file system starting at directory 0, you go down the tree, and you synchronize everything that you see with your Robinhood backend. The point of this is that RBH sync is fundamentally a single-threaded program. So there is not much parallelism going on there. And if you want to achieve parallelism, what you would do is you would launch different processes that would start the scan on different directories. That provides you with a fair bit of parallelism, but you would have to know beforehand how your file system is structured, so that you don't. If you use the heuristic that I described here, you have to know that in advance that your file system is pretty well balanced. Otherwise, you're going to launch a process, and maybe one of the directories in the root directory of the Lustre file system is going to be it's going to account for half of all your files in your file system, and performance-wise, you're going to be slowed down because of this. Let's look at performance. So this example translates in terms of parallelism to this sort of partitioning. So here, with a somewhat pretty well-balanced file system, this would provide you with a good a good level of parallelism. And let's look at performance. I ran my benchmark on a test system which ran on one node with 16 cores. I used Lustre on RAM, which means that I had loop devices which were backed by files in my in dev SHM. I had one entity, 8 OSDs. I always flushed the cache before running my commands. And the file system structure was very well balanced. I used 4 levels of directories. Each directory contained 16 entries, and the 5th level of entries was only files of 1 kilobyte each. The scanning performance, I compared 3 different tools: the RobinHood-v3, so the version 3 of RobinHood, the version 4 of RobinHood, and Find-ls, because Find-ls is pretty representative of what a scan in RobinHood does. All these programs were parallelized with the same heuristic. That's to say, launch one process per directory under the root of the Lustre file system. So for each of those numbers, there were 16 processes running concurrently on exactly the same number of files and directories. The result is that we can see that RobinHood-v3 takes about 5 minutes to complete. RobinHood-v4 does about 2 minutes, so more than twice faster. And it's very close to the performance of Find-ls. The difference between the v4 and Find-ls is probably that RobinHood still has to output and update a database during the scan, while Find only has to print on its the output on your console. But that's a pretty good number, I think. The next application is RobinHood Find. So, of course, after you've populated your database, what you probably want to do is query it. And that's what RobinHood Find allows you to do. It's basically a clone of GNU Find, except that instead of a file system, it queries a RobinHood backend. The usage looks very much like regular Find, except that instead of a path, you would use a RobinHood URI. The rest of the command line is exactly the same as regular Find. So this is an example. You would run RobinHood Find on a RobinHood backend of the type Mongo. The file system's name would be Scratch, and you would query the file system, the RobinHood backend for every file that starts with an A and print them out with no character in between them. In terms of performance, I used the very same file system populated by a previous run of RBHsync or RobinHood-scan, or there is actually no backend for Find, so it was just Find. The performance of RobinHood-v3 was so, we have to say it was so bad that we can't really see much on this graph. It mostly comes from the fact that RobinHood-v3 spends more than 95% of its CPU time querying the database to build paths for the files that it is going to show you on the command on the console, and that impacts performance tremendously. And so I thought that it wasn't very fair to compare v3, v4 Find with this. So I simply patched the RobinHood version so that it wouldn't query paths anymore, and this gives us much more reasonable numbers. And so the performance of the v3 with the patch is only 3 minutes and 17 seconds, which is still more than Find, but to the defense of RobinHood, the more entries you actually output on the command line, the more time it's going to take RobinHood. So if you query RobinHood in such a way that you only have to output tens, hundreds, maybe even thousands of files, you're going to be fine. This is an RBH Find without any filtering associated with it. So that's basically printing out 1 million file names on the command line. And for that, RobinHood-v3 is not very good. At least it's not as good as Find. If you restrict your filters so that you have less and less entries, you're going to get much better performance with RobinHood-v3. But still, RobinHood-v4 is doing very well. It clocks at 10 seconds something, so probably like 20 times better than RobinHood-v3. The next application is RBHFS event. This is the application that applies file system events on a Robinhood backend. So file system events are basically the translation in Robinhood semantics of the changelog records of Lustre. But this one is still on the to-do list. It's not even started. So I don't have much to say about it, except that we have a design, we have a prototype, it looks great, but the numbers are not set in stone, so I'm not going to show any here. Instead, what I'm going to do is I'm going to present the design of how it's probably going to work. And so that brings me to changelog processing. And before I explain to you what we're going to do, I should explain you what we're currently doing. So a basic setup for Robinhood to ingest changelog records is this one. So you have an MDT, you have a node that's both a Lustre client and a Robinhood client, and you have your MySQL database. And the Lustre client, the node in the middle, is charged with the task of getting changelog records out of an MDT, converting it into a query for the database, and pushing that query to the database. There are two problems with this setup, is that if you want to use only one node for many MDTs, if your MDTs are very loaded, for example, if there are spikes in your production, something like this, it's possible that your Robinhood node is not going to be able to handle this load. So that's the first problem. Obviously, the solve to this would be to associate a different node per MDT. And in that case, what you're going to get is probably a waste of resources if one of your MDTs is not using all the power of your secondary node. What we plan to do is to use Kafka to solve a bit of that problem. With Kafka, we would be able to have a Lustre client still pull the changelog records from the MDT. By design, you cannot have more than one Lustre client reading changelogs from an MDT. I mean, you can have several of them, but ultimately they have to pay the same CPU time to fetch the records. So it's almost not a problem to just trim the events through a single node and push this to a Kafka cluster that will process them correctly. And you can see that there is one more color on this slide that on the previous one, I introduced a new rules in the pipeline of changelog processing, which is the Lustre client that simply runs stats. So in changelog records, you don't have all the information that you need to update a Robinhood backend. And so you have to have somewhere a Lustre client that will enrich their changelog records and turn them into actual queries, database queries, which you can forward to Robinhood clients, which can then forward them to the Robinhood backend. The power of this new setup with Kafka is that you can try different setups that would better match your needs. For example, this is probably a good solution to the imbalance problem that I presented a few slides earlier. The one where one MDT is not producing enough changelog records all the time. You're still wasting, it might look like you're still wasting a few nodes. For example, here there are 5, in the previous slide there were 2. So how is this not wasteful as well? Where you can use much smaller nodes. You don't have to provision them like you would for a regular Robinhood pipeline. And by mutualizing the power of the 2 orange nodes, you can actually perform more efficient less wasteful processing. And obviously, if your file system is not very loaded, you can even try and put all the different rules on a single node. It's supposed to work. And that's the end of my presentation. Thank you.
Do you have any questions for Quentin?
Hello. I was interested when you had the performance between the RobinHood v3 and the v4 slides. So you were saying how with RobinHood v3, there's a lot of time spent looking up the path in the database. And I was just kind of interested how you're tackling that in v4. Like, is a lot of the improvement just from the back end, something about the architecture of the back end, or are you doing something differently with how you store the data in the back end?
So in RobinHood-v4 right now, we don't do full paths. That's a bit of cheating. The way I'm planning on solving this is to have paths directly in MongoDB documents. So basically the cost would be a constant. So the performance would look much like this one. The risk that you run doing this is that your path will not be always up to date. So you may have a path that is not even coherent with what you existed at one point in your file system. You might have paths that never existed on your file system, but RobinHood being an eventually consistent system, at some point you will have paths that make sense.
And would that benefit like subdirectory queries as well by storing that? Or is that still like an expensive operation? So like queries where you say, look under this subdirectory and then a bunch of other kind of size and time and so on. Because that's quite an expensive operation at the moment. But is that something that, like you're saying, if you're storing the path in a document, is that quicker to look up now?
Yeah, so right now what RobinHood v3 does is that it runs a procedure on the SQL server that computes path by recursively traversing the entries and going back to the root of the file system. With RobinHood v4, if you store the path directly into the MongoDB document, you can get it for free when you get the document back. So the cost is pretty good. Obviously, there might be a need to have sort of like a more consistent path, which would do pretty much the same work as what RobinHood does now, but by default, you would use the path that's embedded in the document. I hope that answers your question.
Yeah, that's great. Thanks.
Okay.
Other questions?
All right, thank you. Then the code is on GitHub. We're in the branch v4. That's not including the tools, but otherwise you have the core library that I use for the tools. Thank you.